Very good morning to everyone. I am Mari Uray, technical trainee at Wings of Aero. It is a glorious moment to expand my warm wishes to on behalf of the Wings of Aero. I would like to explain about the TEMS Terra platform and our previous chief guests. TEMS is an Indian digital learning platform that provides advanced learning and research opportunities for science and engineering students. These are our previous sources. Mr. Mitch Hunter Storian, founder and chief executive officer at Asteroid Minion Corporation Limited, UK. He was delivered his session Asteroid Minion on our platform. Mr. Manuel Ratna, research interests include the development of robotic technologies to support astronauts training and enable human exploration of Mars and the Moon. He was delivered his session Robotics for Future Space Exploration on our platform. Dr. Mohammad Sadri, Associate Professor at Southern New Hampshire University, Southwest New Hampshire, US. He was delivered his session on recent research on UAV on our platform. Today our chief guest, Mr. Swagat Mishra. First of all, I wish to convey my heartfelt gratitude to Mr. Swagat Mishra. Theoretically, cosmologist working as a senior research fellow at Eastern University Center for Astronomy and Astrophysics, Pune, for accepting the invitation and presenting over the seminar on Primordial black holes from the Big Bang. The webinar was conducted and organized by the Wings of Aero for the science and engineering students to gain insights and information that would remain effective in their research and our project. I will give the session to the Mr. Swagat. Sir.
Hello.
Yes, sir.
Hi. I think I'm audible, right?
Okay, sir.
Great. So I'm going to share my screen. Please let me know if my screen is visible.
Yes, sir.
Great. I'm going to make it full screen now. So let me know if full screen is also visible.
Yes, sir. Visible, sir.
Great. Thank you very much. Hello, everyone. Good morning. I am Swagat. I just finished my PhD in physics in last December, and I work on early universe physics mostly about how our universe was born and how it evolved and all that. I'm going to talk a little bit about that, but mostly today I'm going to focus on primordial black holes, uh, which we can call as black holes from the Big Bang. Okay, so there are two names here basically, black holes and Big Bang. So these are two topics that we're going to discuss today during my lecture, and I'm going to try to make things a little simpler because this is a very technical subject. But if anybody wants to understand some of the technicalities, please let me know either after my lecture or write to me. I'll provide my email ID. Okay, so let's put all that aside and let's just start talking about the topic today, which is primordial black holes from the Big Bang. Okay. So before I come to black hole, I'll first talk about Big Bang or our universe first. Uh, if suppose we had a very wide angle camera, okay, or maybe we are some superhuman beings and our eyes can see in all frequencies. Suppose it's a hypothetical situation, and it can see a big portion of our entire universe. Okay, so we have a very wide angle view. If you look at our universe like in a wide angle view camera, like a bird's eye point of view, our universe is going to look like this. Okay, if you didn't know this before, this might just surprise you. This looks nothing like our universe, but it is what our universe would look like from the larger scales. Okay, and here what you see is you see some kind of threads. Okay, white color threads running around, filaments, and in between you see some voids. Okay, you see some voids. So what you see this is like a three-dimensional spider web. Okay, in fact we call it the cosmic web. This is how our universe will look like. each white dot here, there's so many white dots, no? Each white dot here, any small dot you take, is like a galaxy, okay? And each thick filament here is like a cluster, super cluster of galaxies. Okay? So there are so many galaxies in any portion of our universe. In fact, I can go to any particular part, let's say this small part somewhere here, and I zoom in. So rather than having a wide angle view of the universe, I could just zoom in and see what it looks like from a little smaller angle, which I'll show in the next slide. But let me tell you that this is not an actual image, because we don't have such a wide angle view. This is a computer generated simulation, okay? But our universe will look pretty much like this. So if I now go to any small part, whatever part you choose, let's say this part, and just zoom in, then our universe is going to look like this, okay? Now this is a more familiar picture. Let me explain you what it is. It is a very tiny angle in the sky. This is a real picture. This is not by computer. It's a photograph taken by Hubble Space Telescope. If you go to sky in some direction, you look at the sky in a very tiny angle, okay, smaller than a degree, 1 degree. What you're going to see is this. You see that the sky within the 1 degree angle is filled with so many galaxies. Okay, there are many galaxies here. Each circle here is a galaxy. Okay, so each galaxy is made up of several stars, 100 billion stars. So, which seems that our universe today is really filled with galaxies and galaxies. So our universe is a place of galaxies. Okay. Yeah. Now this is how our universe looks today. If we zoom in, and if you look at our universe from the bird eye point of view in a wide angle camera, it will look like the way I showed you, like a cosmic wave. So that's a universe looks like. Now you can ask the question: does our universe evolve like a human being evolves? Like if you look at a human being today, a human being looks like a particular way, but when the person was born as a child, the same person looked very different. Okay, and as time progressed, it evolved to this state. So is it true for the universe, or is our universe eternal and static? That our universe is never changing, it is just there forever, it doesn't change, all the galaxies are just there? The answer turns out to be our universe is evolving. Okay, so what happens if you look at all these galaxies? There's not just there, they're all going away from each other. All the far away galaxies are going away from each other. Okay, so if you turn the clock backwards, you will see that in the past, all the galaxies would be closer and closer and closer. There will come a time when all the galaxies that we know of were so close that everything was a dense pack. It was so dense and so hot that atoms cannot remain in this atomic form. Okay, so high is the energy and density that electrons will come out of nucleus. So the universe will remain in a plasma state. So it turns out, if universe is expanding today, which we know, then in the past universe should be in a plasma state. Okay. So here is a brief history of our universe. If I was giving a lecture today on the Big Bang Theory, I would have talked a lot about this. But since we are mostly talking about black hole, I just introduced it in a little bit. So let me tell you briefly what it is. It turns out at the very early time, somewhere here, okay, our universe was in a plasma state. Plasma state means protons and electrons were separated. Okay, they were not like in an atomic form. So all the nuclei are separate and electrons are separate, and they're moving around in a dense pack. Okay, and everything was in a thermal equilibrium. And then as universe was expanding gas usually cools down. So as universe expanded, it cooled down a little bit. And when the temperature dropped below the ionization energy of electrons, then electron could combine around protons to form hydrogen atoms, or it could combine around the helium nuclei to form helium atoms. Okay, so then we have hydrogen and helium atoms in the universe. And before this phase, so before these atoms were formed, since universe was in a plasma state, a plasma is an opaque substance. Okay, you know it because you can look at the sun, our star, sun. A sun is in a plasma state today, and it is opaque in the sense if you look at sun, you just see the surface, you don't see what is inside, right? Because light from inside is directly not coming to you, because the plasma is opaque, so it's like fuzzy. So universe was completely fuzzy. Okay, and but once atoms were formed, light could travel freely. Okay, it was no more trapped. That happens because neutral gas doesn't absorb light that much. Example of this is that you can see me you can see my face through your camera or through your screen, because light from my face is entering this camera, this webcam, without any hindrance, even though there is air in this room. Okay, so once universe became neutral at this point, okay, here, once it became neutral, then light could travel. Okay, so this trapped light, which was trapped in a plasma, was in a thermal equilibrium, and once universe cooled, the light started traveling. So we see a thermal distribution of light, or a black body radius. We should see it if universe was in a plasma state, and it turns out we do see it, and it is called cosmic microwave background radiation. Okay, so this light is filling the universe today everywhere. So once universe then became atomic size, these atoms, so we have now atoms and molecules form slowly, and universe is expanding. But what is happening is, wherever there was a little high number of atoms, they would start collapsing, and slowly they will form stars and all. And over 13.8 billion years, we have the present universe, where we have galaxies. Okay, so again, to summarize, you started up in a plasma state, universe expanded and cooled down, all the gas, so you made a transition from the plasma to the gas state, and then finally universe, this gas started collapsing onto each other and started forming stars, and the stars formed galaxies, and today we see the universe in this web structure which I showed you. So that's the history. Okay, now what all our universe is made up of? Okay, our universe is made up of photons. Photons means light, electrons, as I am talking about, because electrons are everywhere, nuclei, protons and neutrons basically, as well as neutrinos. Okay, so these are the particles that we know of, and universe, or that we know of, that they're there on Earth, they're also there in the universe. So universe is made up of all these particles, as well as there are two new things in the universe, something called dark matter. It has a property that it helps to clump these atoms. Okay, so once universe went from the plasma state to the atomic state, dark matter helped it to sort of cluster, clump, and then form galaxies. Then there is something called dark energy, which is like a repulsive gravity. Okay, so if the universe is filled with dark energy, it's going to repel the universe. So as universe expands, rather than slowing down its expansion rate, dark energy is going to speed up its expansion rate. So if you look at the size, this diagram shows the size of the universe as a function of time. So if you look at the size, universe was expanding, then slowed down for a long time, and then started speeding up down, accelerating. Okay, so our universe is accelerating today. Its size is increasing faster and faster, and that's because of dark energy. But again, these two things are not important for our talk today. So I just mentioned it a little bit. Especially dark matter might come up later in the talk. So dark matter is some substance, some heavy substance in the universe, and the aim of this substance is to help cluster and form galaxies. Okay. In the history, let me put some time scales which I didn't tell you. So if I go to a time, so today our universe is 13.8 billion years ago, billion years old. Okay, our universe 13.8 billion is quite a big age. But if you go back in time, when universe was less than 1 second old, okay, so very early universe. At that time, the first nucleus started to form. In the sense that before that, universe was in a quark plasma state. So quarks were floating around differently. But around 1 second, the first nuclei started to form. So quarks came together and formed protons and neutrons. Both hydrogen nucleus, which is just a proton, or helium nuclei, which is combination of a proton and neutron, started to form. Okay, combination of two protons and two neutrons started to form. Then when the age of the universe, so this was at 1 second. So by 1 second, you started to form nuclei in the universe, okay, atomic nuclei. And around 4 lakh years, okay, when universe age was 4 lakh years, that time, universe made the transition from the plasma state to the neutral atomic state. And so the light trapped in the universe was emitted at that time. Okay, so that's another important time. So these are very early universe. Okay. Now in the plasma phase, if we go to the plasma phase particularly, so here from the beginning up to this part, this small part was the plasma phase. Okay, it was only for 4 lakh years. Okay, since then 4 lakh years to 13.8 billion years, universe has been in a different state. Okay. Now in the plasma state, a lot of particle physics phenomenology was going on. Okay, particularly. So there are universes filled with quarks and with electrons, with photons, with neutrinos, with dark matter particles, and they're all interacting. and then slowly nucleus started to form, and slowly after nucleus formed, then slowly electron combined with the nucleus, and then the light was emitted at that time. Okay. Anyway, I just wanted to stress this point. It was an important point. General conclusion: universe, the entire universe, okay, not a small part of our universe, the entire universe was in a plasma state. Okay, and slowly as universe expanded and cooled, atoms and molecules formed in the universe, and then slowly these atoms and molecules started to clump together and then form stars and galaxies. And once you have a big star, the star is burning its fuel, so it's burning hydrogen to helium, helium to beryllium, and all that way. And once it is out of all its fuel, the star is going to die because gravity is trying to collapse it, but the burning of the fuel was trying to keep it intact, in the sense that a star is burning the fuel. So because of this fuel, energy is going out. Okay, so energy is going out while gravity is pulling in, so there is an equilibrium. But once it stops, its fuel is over, it doesn't produce any energy, so it can fall inward. So a star might die by collapse. Okay? When the stars collapse, particularly when big stars collapse, what can happen is they form black holes. Okay, so we came to our topic from black holes. So from plasma state of the universe all the way to big stars, and then death of big stars to black holes. And this process, this whole process takes hundreds of million years. Okay, so the first black holes in the universe, if they form in this way, they actually form after 100 million years or so, at least after 100 million years. Okay, these black holes, which are formed by the death of stars, we're going to call them astrophysical black holes, okay? Because they are formed from astrophysical object like a star. Okay? And since these black holes are formed by collapse of stars, their mass, the mass of such a black hole, astrophysical black hole, which is formed by the collapse of a star, has to be at least the mass of a star, in the order of mass of a star. Okay? So every time I call mass of a star, I'm going to call it solar mass. The solar mass is basically mass of our sun, okay, which is 2 into 10 to the power 30 kg. It's quite a big mass, no? 10 to the power 30 kg. So these astrophysical black holes are there in the universe, and they have a mass necessarily greater than a solar mass. Okay, so please remember this fact. Okay, now these are astrophysical black holes. Now in general, okay, I told you astrophysical black holes, they form by the collapse of stars. But what is a black hole? Okay, well, what is a black hole? So you take some mass, any mass. Okay, you take any mass, m amount of mass, and you keep compressing the mass. Okay, by some mechanism, you compress it. When you compress m amount of mass to a small size, such that the size of this mass becomes smaller than this formula. Okay, so if I give you m amount of mass and you make it size smaller than 2gm by c square. Okay, g is the Newton's constant of gravity and c is the speed of light. If you make it this way, then the gravity of this object, it's so compact, its gravity will be so strong that nothing can escape this object. Okay, that becomes a black hole. So if you throw light on this, light will fall into it, but it cannot escape. Okay, so that's why it's called black, because you don't get light out of it. Okay, it looks black. That is a black hole. That is the real definition of black hole in physics. Now, whatever way you compress is a separate issue. But if you can compress a big mass to a very small volume, that's called a black hole. So black holes are regions of space-time where the curvature is high, which you can think of as the density, mass density is very high. Okay? So you have a large amount of mass and energy condensed or compressed into a small region. So again, keep this in mind. This is a very important thing. A lot of people don't realize. If you ask them what's a black hole, they will say, oh, when a star dies, that's a black hole. That's a formation of the black hole. But the definition of the black hole is that a lot of mass in a small region of space, okay, compressed object. Now, what could be the mass of a black hole in general? Well, as long as you can, I can give you any mass. I can give you this coffee mug. If you can compress it to a very tiny space, it will become a black hole. So as long as you can compress, it will become a black hole. So mass of a black hole can be very low. Okay, yes, 10 to the power minus 5 kg, or it could be very high, like hundreds of billions of solar mass. Okay, so these are huge black holes. Then there could be tiny black holes. This is in principle. Now this m dot. Okay, I'll be using this m dot symbol. So be clear that when I write m dot, it means mass of our sun. okay, which is 2 into 10 to the power 30 kg. So black hole could be 10 billion or even 100 billion times mass of our sun. Okay, it could be huge, or it could be a very small, like 10 to the power minus 5 kg. Whatever be its mass, its size typically is smaller than this formula 2 gm by r. Okay, I'll tell you what the typical sizes are. Now, what are black holes that we have observed in nature? Okay. First thing, do these black holes exist in nature? Answer is yes, 100% yes. We have observed many of them, thousands of black holes. Okay. So what kind of masses have we seen? Well, we have seen some X-ray observations as well as gravitational wave observations. We have seen that there are black holes of mass ranging from 3 solar mass, 3 times mass of our sun, all the way up to 150 times, 160 times mass of our sun. Okay, so there's a group of black holes. These are given by these there's purple dots here and the blue dots here. Okay, these are the several black holes that we have seen in this mass range. Okay, it's around 3 solar mass to 160 solar mass. Then at the center of galaxies, especially at the center of very powerful jet engine galaxies, which are called AGNs, we have seen black holes which are even heavier, like monsters. Okay, like their mass is in between 10 to the power 6 solar mass, so a million times mass of our sun, to 10 billion times mass of our sun. These are super monsters. Okay? One of such black holes was reported last year as the image of a black hole. I mean, wow. So what they see is you have some billion solar mass black hole, and around that black hole some gas is flowing. Okay? Because this gas is flowing around the black hole and black hole is pulling them, they're rotating really fast. So they get heated up and then give you light. And you can see that light and see, okay, the gas is rotating around the black hole. So that is what is wrongly called image of a black hole. But yeah, that's a black hole which is really monster. Okay. So all these masses we have observed. But we have never observed a black hole whose mass is smaller than mass of our sun or mass of a star. Okay. So all the black holes that we have seen have mass greater than mass of a star. So it seems like black holes are formed by collapse of big stars. Because if you have a big star, it collapses, then its core will form a black hole. And since you form black hole from a big star, its mass has to be at least mass of a star or greater. It could not be small. What we're talking today are about black holes which are not formed by the collapse of stars. So star collapse is one way of compressing a big mass into a small volume. But maybe there are other way of compressing things by which you can compress even a small mass like this to a tiny volume, or even huge mass to a tiny volume. Okay. These are the black holes that are called primordial black holes, and we're going to talk about that now for the next 15 minutes. If we find a black hole whose mass is smaller than mass of our sun, it'll be incredible. Okay? Because you could find a black hole whose mass is mountain mass, or could be a planet mass, could be an asteroid mass, could be a like say coffee mug mass. Okay, could be anything. All right. So what are primordial black holes? Now these are black holes which are not formed from the collapse of stars. For stellar collapse, you have to wait hundreds of million years, as I told you, because first stars have to form and then they have to collapse. But in general, if black holes formed in the very early universe, already in the plasma state, okay, I told you universe was in a plasma state before 4 lakh years. So if these black holes are formed in the very early universe in the plasma state, we are going to call them primordial black holes. The word primordial, if you have never heard about it, it simply means ancient. Okay, so it formed in the early universe, okay? Not in the late universe by stars. Typically, these stars will be formed, these black holes will be formed when universe was less than 1 second old. So really a baby universe, okay, very early universe. So universe was less than 1 second old, and the temperature of the universe was 10 to the power 10 Kelvin. So 10 billion degrees Celsius, okay, pretty high temperature. So this is the hot dense plasma state of the universe, which is usually called hot Big Bang phase. That's why these black holes are called black holes from the Big Bang, because they formed in the hot Big Bang phase, not in the later phase of the universe. Okay. Since they formed in the hot Big Bang phase and there were no stars at that time, these black holes could have any mass. If you can compress any mass, they could have any mass, these black holes. Okay. Now, even if we detect a single black hole in the universe, which has a mass which is smaller than mass of a sun, It will be a proof that this black hole must have been a primordial black hole, because it could not have been formed by collapse of stars, and it would have formed in the very early universe in the first 1 second. Okay. Now, how can we form them? What happens? How do we form them? Well, what happens is that in the early universe, in the plasma, our universe in the plasma state, it's possible that density of the plasma is not same everywhere. Okay. At some scale, at some length scale, it's possible that density of the plasma is very high at some place and very low at a place next to it. So wherever you have density really high, that high density part, because of gravity, if you have more density, you have more gravity. Okay, it will start collapsing, and it can completely collapse to form a black hole right in the early universe. Okay, so that's the mechanism. So they're formed by the collapse of very large density fluctuations. Now you can ask, what in the universe can create such large density fluctuations so that they can collapse to a black hole? Well, usually it is created by quantum mechanics. If I have time today, right at the end, I'll talk about it for 5 minutes. Okay, otherwise I'll leave it. So remember that, but quantum mechanics has something to do with creating these large fluctuations. Okay, so here is a picture. So you have this plasma in the universe, but at some place, maybe the plasma density was too high, so it started collapsing and finally forms a black hole. Maybe that happens at another place, maybe at another place. So at several places, you start forming these small black holes, and these are primordial black holes. Now you can ask, what could be their mass? I told you they can have any mass, but what in general? It depends on when they form. Okay, if primordial black holes formed in the very early universe, then they have very small mass. If they are formed a little later, then they have bigger mass. But all of them are formed before 1 second. Okay, let me show you numbers which will make it clear. If I give you a primordial black hole of a particular mass, how big it is in size. Okay, if I give you some primordial black hole of some mass, let's say Earth mass, what should be its size and when was it formed in the early universe? This is what I'm going to show you now. The size of a black hole, as I showed you, is usually called Schwarzschild radius. Is related to its mass. So if I give you mass, you know the size. Okay. Typically, if you can stare into this formula, you see that the size of a black hole is 2.95, so 3 kilometers, if mass of the black hole is equals to mass of our sun. Okay. So you know what this means? This means that if you take our sun and you want to make it a black hole, you have to compress it into a size which is only 3 kilometers. 3 kilometers is nothing. It's the size of it's even smaller than size of a city. Okay, so you have to compress the entire sun to a small size so that it becomes a black hole. That's the relation between size and the mass. And what is the relation between mass of the black hole and when it is formed in the early universe? Well, mass of the black hole is around 6 lakh solar mass if it was formed at a time t, which is 1 second after Big Bang. Okay, so when universe was 1 second old, if you form a black hole, that would have a mass of 6 lakh solar mass. Okay. Now, if you form it before 1 second, its mass will be even smaller. So you could have very small mass all the way up to 6 lakh solar mass or even more. If it forms later, it will have even more mass. Typical examples. This fancy name, which you see, supermassive black hole M87, is the black hole whose image has been taken. At least wrongly it is told so. This is the famous black hole. Okay, it has a mass of 6 billion solar mass, and if it was formed in the early universe, not by star collapse, then it should have a size of a solar system. Okay, you have a huge solar mass black hole, and its size will be 10 to the power 10 kilometer, which is like our solar system. It would have formed when the universe was about 3 hours old. Okay, today it is 13.8 billion years old. This is hours old. Okay, very early universe. Okay. Now, if you have solar mass black hole, 2 into 10 to the power 30 kg, it will have a size of 3 kilometer, as I told you. And such a black hole would have been formed in the early universe when universe was smaller than a microsecond. Okay, very early universe. The Earth mass black hole would have a size less than a centimeter. Okay, so you have to compress the entire Earth to less than a centimeter for it to become a black hole. And if such a black hole was formed in the early universe, it would have been formed at the time when universe was 10 to the power minus 11 second old. You could form lunar mass black hole that would have even smaller size and would have formed even earlier. Let me show you a Himalaya mass black hole. So if you take Himalaya mass object and you want to form a black hole out of it, it'll have a size of 10 to the power minus 15 meter. That's the size of atomic nucleus. Okay, so imagine a big mountain has to become, you have to compress it. Mass is the same. Okay, you're not changing the mass, you're just compressing it to a size which is smaller than atomic nucleus. Okay, that would have formed at very early times. So this is very exciting. So that means if you detect a black hole, let's say of asteroid mass, you're talking about what happened in the universe when universe was 10 to the power minus 14 second old. So that's why these objects, primordial black holes, are extremely exciting, because if they exist, they are telling you about very early universe. Okay, look, these so early that we don't know about the universe at that time. Okay, so important thing is that primordial black holes, they can potentially prove the very early universe. Okay, so that makes them very. So let me put the time scales again, if you have forgotten. Know that 1 second, when universe was 1 second old, first nuclei started to form. When it was 4 lakh years old, first atoms started to form. These black holes are formed much before that, much before 1 second. Okay? So, and thus their size is they could be microscopic. Look, some of them have size smaller than a micrometer. So these black holes have size smaller than our cell in the body, or smaller than a bacteria. Okay, smaller than a bacterium. So it's really tiny. Okay, since these black holes are heavy, so these black holes are heavy because they could have big mass, Himalaya mass, Earth mass, solar mass, and their size is small. So quantum mechanics as well as gravity both are important for these black holes. Okay, so here's an example where both quantum mechanics as well as gravity important. So Stephen Hawking started to work on what happens if you apply quantum mechanics to these black holes, which are really small, and he found that classically, if you don't apply quantum mechanics, you expect that a black hole is black. So if you have a black hole around, whatever light is going inside the black hole is not coming out, okay, because it has so strong gravity. But what Stephen Hawking found, that quantum mechanically, things are going to come out of this black hole once in a while. Light is going to leak out, or what we call in physics tunnel, quantum mechanical tunneling. It's going to tunnel out of the black hole. So Hawking found that, okay, even though black hole is classically black, quantum mechanically it's not black, it's radiating light. Okay, so a black hole, rather than looking black, could actually look like glowing. Okay, could be glowing in orange light, could be glowing in infrared, could be glowing in X-ray, could be glowing in UV, depends on the mass of the black hole. So let's see. Yeah. So if Hawking has claimed that because of quantum mechanics a black hole is going to radiate, if I give you a mass of a black hole, given mass you also know the size, what color light comes out of this black hole? Okay. Now Hawking said the light that will come out of it is a black body radiation. So it has all sorts of colors. But it will peak, a black body radiation peaks at a particular color. So which color it will peak? Okay, that's important. So what Hawking found is that this light which is coming out of the black hole. So usually if you have a black hole, then usually nothing should come out of it. But once in a while, some particles leak out of it. Okay, that's Hawking radiation. And the temperature. So this object, which was supposed to look cold and dark because it's a black hole, is actually not cold, it is hot because it has temperature. Like sun has a temperature, no? So surface is glowing because light is coming. This also has a temperature. And the temperature is given by a fundamental formula. I just want to stress that at least people who know physics see that this formula for Hawking temperature of a black hole, has Planck constant h, speed of light c, gravitational constant g, and Boltzmann constant K Boltzmann. So this is a formula where you have quantum mechanics, which is Planck constant, special relativity, so you have speed of light, gravity, so you have Newton's constant, as well as thermodynamics. Okay, so K. It's an equation which has all branches of physics. Okay, very important equation. And the temperature, I can calculate these quantities, and Hawking temperature turns out to be 6.2 into 10 to the power minus 8 Kelvin if the mass of the black hole is equals to mass of our sun. So if you take our sun and compress it into 3 kilometer radius, then it becomes a black hole. And if you wait, ultimately light is going to come out of it. A thermal radiation is going to come out of it. and that temperature is extremely low, 10 to the power minus 8 Kelvin. That temperature light is basically mostly radio waves. Okay, so very long wavelength radio waves are going to come out of that. It's very difficult to determine this temperature. No? This is 10 to the power minus 8 Kelvin. No thermometer can detect it. So that's why Hawking temperature has not been detected yet, because I told you all the black holes that we have detected until now, they have a mass greater than mass of our sun, but greater is the mass, bigger is the black hole, so smaller is quantum mechanics, quantum mechanical effect, hence smaller is the temperature. Okay. So big black holes are big size and they have small temperature. Small black holes are small size but they have high temperature. Okay, so that's Hawking radius. So, but since we have only seen big black holes until now in the universe, we have not tested Hawking radiation. That's why Stephen Hawking died without getting a Nobel Prize, because we have not tested it yet. Okay, but Hawking radiation is testable for subsolar mass black holes. In the sense, if the mass of the black hole, this mass of the black hole is much smaller than solar mass of the sun, then Hawking radiation temperature could be very high. It could be so high that we would see it either in infrared or in visible or in UV or in X-ray or in gamma ray. Okay, depending on the mass, of course, the temperature would be accordingly higher. So that's great. So we could test Hawking radiation if we detect a primordial black hole. Now, since a black hole is radiating in Hawking's theory, it's radiating out, its mass is getting lost into this light. Okay, so the mass is decreasing. And we can calculate how long it will take for a black hole for all of its mass to evaporate out completely. This process is called usually Hawking evaporation. Okay, it simply means losing mass by light, by radiating light. If the mass of a black hole is around 10 to the power 15 gram, okay, now 10 to the power 15 gram is Himalaya mass. So if you take a Himalaya mass black hole, Himalaya mass but size would be smaller than atomic nucleus. Okay. Anyway, if you take Himalaya mass black hole, it's going to radiate out in 13.8 billion years exactly. So if I form a very tiny black hole, it will radiate, and in 13.8 billion years, which is the age of the universe, it will evaporate out. But if I take a black hole which is even smaller, that will have even higher temperature, so it will radiate even more, and it will not last until today. So if these black holes were formed, very tiny black holes were formed in the early universe, they will not last until today. They will just radiate out. Okay. If some of you were alive or aware in 2008 when the Large Hadron Collider was being switched on, a lot of people were concerned that what if black holes are formed in this collision? Will it eat up the Earth? But the answer was no, because if they are formed, they will be so tiny that they won't even last for a second. Okay, they will just go. They will be Hawking evaporating and gone. Okay, great. So let's talk a little bit about implications of primordial black holes. So suppose we have these primordial black holes in the universe. They formed in the early universe, in the hot Big Bang phase, and suppose their mass was big enough so that they have not evaporated until today. So they are there. What can they do? Well, first thing, they can act like dark matter. Remember, I introduced you dark matter. These are heavy objects in the universe which help to clump things. Okay, so we could have these primordial black holes, a lot of them in the universe, and they can help to clump and form galaxies. So they can act like dark matter. So it's possible that what we call dark matter are nothing but just primordial black holes, or maybe some fraction of the dark matter is made up of primordial black holes, and other fraction is made up of some other exotic particles. That's also possible. Second thing, that the gravitational wave of observations by, let's say, LIGO and Virgo are observing collision of black holes of different mass. They're observing collision of black hole of 10 solar mass, 20 solar mass, 50 solar mass. Now, what these black holes are? They could be astrophysical. They could also be primordial black holes. Now, astrophysical black holes have the issue that suppose I have two big stars, okay, and these big stars are rotating around each other. So they have to form black holes. Okay. Now, when they form black hole, when they die, these stars, they go through supernova. When they go through supernova, it's possible that they blow each other out. So to get a binary system of black hole is a difficult problem. In fact, this is one of the most difficult problems nowadays, and people are working on it. How do you form black hole binaries? Because these binary black holes will rotate and give rise to gravitational waves, which we are detecting. Okay. Maybe these black holes were primordial black holes. They were not formed from stars, so they were just early universe. You have so many primordial black holes. Two of them came together and started rotating. So many such pairs formed. Okay. Third thing, I told you these big galaxies with powerful jet engine have monster black holes at the center. Now, if black holes are formed by collapse of stars, a star mass would be like 10 solar mass, 100 solar mass. How come we have black holes which are like billion solar mass? Okay. So it turns out a billion number of solar mass black holes came together. How did they come together and form? This is also an unsolved problem. It turns out maybe a primordial black hole, when it is formed, so let me go back to the time. If a primordial black hole is formed around 1 minute or so, then it could have a mass, or 3 hours, it could have a mass really which is really high. So it could be a primordial black hole then. Okay, it could form directly with a high mass. So you don't have to form first a star and then small stellar mass black holes and then keep combining them to form billion solar mass black holes. You can directly form this high solar mass black holes from primordial black holes. Okay, that's one thing. Other thing is it can prove the physics of the very early universe. As I told you, they are formed very early in the universe. So if you detect them, you know what was happening in the universe at that time. Okay. Next, they can probe or test Hawking radiation. Because Hawking radiation temperature is usually so low for heavy black holes, for light black holes or primordial black holes, they could be really high temperature and then you can detect them. Okay. Also, it turns out primordial black holes have something to do with planet 9. It may be. So let me tell you what is planet 9. So we have 8 planets. Forget about Pluto. We have crossed out Pluto. So we have 8 planets. There are a lot of objects which are outside Neptune. Okay, these are called trans-Neptunian objects. And these objects, the way they move around our sun, they look like to be. It seems that they are aligned in a particular way. All their path is aligned in a particular way. So from there, it seems there is another object out there whose mass is around 5 to 10 Earth mass. So really a big object. Okay, and the gravity of that object is causing these paths of small objects outside Neptune's orbit to align. Okay, so that's the hypothesis, and people are looking for this 5 to 10 Earth mass object. It will be a planet, of course, because it's really big. But we have been looking at them in telescopes and trying to see the light emitted by this object, but we are not seeing any light from this object yet. So maybe this is a black hole. Okay. Now, a 5 to 10 Earth mass object cannot be a astrophysical black hole, because the astrophysical black hole has a size has a mass of solar mass, but this is much smaller. This is the Earth mass, so it could be a primordial black hole. If it is a primordial black hole, it will have a size like this, 2 centimeter, 3 centimeter. So its size is as big as this dot. So there was a paper in 2019 which said that maybe this is a primordial black hole, and then you can read up. There are many other papers which talked about if it is a primordial black hole in our solar system, how can we send probes and test it and all that. I just said because if you are engineering student, you might be interested in this kind of stuff. Okay. So what do we know about these primordial black holes? Well, observationally, we have not found any evidence of this primordial black hole yet. It doesn't mean that it doesn't exist, but we have not found a single primordial black hole yet, and we are looking for it. I can describe this graph, but it might become too technical for people, so I'll leave it. Unless anybody is interested, I'll explain. Otherwise, I'll leave it. But it just says how many primordial black holes could be there, and here is the mass of the black hole. It turns out and whatever region has been shaded out, either by gray color or by orange color, their primordial black holes cannot exist. So, for example, if you take a 10 to the power 15 gram primordial black holes, there cannot be many of them. And if you take a very heavy black hole like 10 to the power 5 solar mass or so, there cannot be many of them. But you could have some mass, let's say 10 to the power minus 10 to 10 to the power minus 15 solar mass primordial black holes. There could be a lot of them. Okay. How do we detect these black holes? Well, there are several techniques. First thing is from gravitational waves. So if you have very tiny primordial black holes, and if 2 of such black holes come together and rotate and collide, they'll give rise to gravitational waves. Or from the Hawking radiation of this. So you have many such black holes, they're all Hawking radiating. You can see the radiation and figure out if they are there or not. They can also do gravitational lensing, in the sense that there is a star and this black hole passes in between the star and us. The starlight will be lensed because it has a very high gravity, this black hole. So we'll see a rise in the intensity of the starlight, and from there also we can detect. So we are searching for them by several future observations. and in next 10 years, let's hope to detect some of them. Okay, the formation of these primordial black holes. I've finished most of the things that I wanted to say, but I'll just focus on a little couple of things. Formation of these primordial black holes. I told you to form black holes in the very early universe, you need a high density fluctuation in the plasma. So universe has plasma in the early universe. Then you need a region where you have high density of the plasma and next to it low density, so that the high density could really collapse. Now, what can create such a large density fluctuation in the universe? Well, it's usually quantum mechanics which can create. I'll talk about it, maybe since I have time, I can talk about it for next 2 minutes, maybe 3 minutes. But if you want to read more about it, I will recommend to read this, where I actually explain here in simple language how you can form from quantum mechanics. Okay. Well, let me try and explain a little bit. So these are extra things. So I told you our universe is expanding. Okay, as it's expanding, it's cooling down. Okay. Now, for most history of the universe, this is a time when universe was about 1 second old, to a time when it's about several billion years old. So for most history of the universe was decelerating. So it was expanding and slowing down. So universe was expanding, then the rate of the expansion was slowing down. Okay. Recently, universe has started to speed up. Okay, that is because of the dark energy. This is the history of the universe. But if I go to a time much smaller than 1 second, okay, so I go to very early universe, much smaller than 1 second. There, it seems that there was a period when universe was also accelerating there. Okay, it was accelerating so fast that within a fraction of a second, the size of the universe increased by 10 to the power 25 times. In one fraction, universe became 10 to the power 25 times bigger. Okay. So that phase of ballooning or inflating is called cosmic inflation. So let me talk about cosmic inflation. So it's an accelerated expansion of space in the very early times. So at very early, universe expanded acceleratedly and then expanded slowly and decelerated. Okay. That slow decelerated expansion phase is called hot Big Bang phase. So this was before the hot Big Bang phase. Now, when universe accelerates very fast, what happens is quantum mechanics becomes very important, and this quantum mechanics creates density fluctuations. So it doesn't make density constant everywhere. It makes density higher somewhere, lower somewhere. Okay. It turns out that density could, on some scales, the density fluctuation could be low, in the sense that the difference between density here and the difference between density there is some difference, but the difference is not much. If density is 1 here, density will be 0.999 here. Okay, very small difference. But there will be some places, especially at small length scale, it's possible that density is very high here and very low here. Then here it will collapse to form a black hole. Let me explain this statement in a picture, which I think all of you will understand. Now, when I say density fluctuations, I say, or anybody says in physics, what do you understand? What you say is that suppose I have density as a function of space. Just look at this part of the graph, this black part. If density as a function of space has a fluctuation in the sense that there is an average value given by this dotted yellow color line. So there is average value, and around that average value, density is varying from space to space. So this is space in x-axis. Okay, so as I go to different space points, density is slightly up, slightly down, slightly up, slightly down. So it's randomly fluctuating. This is what called a density fluctuation. Okay. Now this fluctuation of densities, this random function which looks like random, it could be written as a big sine wave. So a sine wave of some wavelength or some frequency, then another sine wave of higher frequency, then another sine wave of even higher frequency, and so on. This is basically Fourier analysis, if people who know it. So any random fluctuating function is a combination of some a1 times sine 1x plus some a2 times sine 2x plus some a3 times sine 3x, and so on. So basically each sine x with frequency k has an amplitude ak. So for example, this has frequency 1 and it has some amplitude or height. Okay. This has frequency 2, it has some height. This has frequency 3 and it has some other height. So in general, the height or the amplitude would change with frequency. Okay, that's a very important quantity. So if density is fluctuating like this, density is same almost everywhere, but somewhere little higher, little lower, little higher, little lower. And we want to see them in terms of many waves. Okay. Now here what I have plotted is the amplitude of a wave. So I have a random density fluctuation. It is composed of a long sine wave, then a short sine wave, then even shorter sine wave. So I'm studying as I increase the frequency or make the wave shorter and shorter, how the amplitude changes. Okay? This is a square of the amplitude. It's called power spectrum or power. It turns out the square of the amplitude could increase as I go to higher frequencies. So smaller waves will have larger amplitude. That's possible. Such a thing is called blue tilt, okay, because it's increasing or bluing. Okay, I mean the frequency is increasing, so blue light has high frequency. Similarly, the amplitude could actually decrease as the frequency increases. So that is called red tilt. Okay, or the amplitude could almost remain constant. So all sine waves contribute as equal amount. Okay, so a1 times sine x, same a1 times sine 2x, same a1 times sine 3x, and so on. Okay, there are three possibilities. Now it turns out for our universe, if you look at big waves, so our universe has density in the early universe. There is density fluctuations. So density is not constant everywhere. There's somewhere high, somewhere low. And we want to understand how that fluctuation is made up of big waves and small waves. If you look at very big waves, waves which wavelengths are really long, there the amplitude of fluctuation is small, very small, like 10 to the power minus. Amplitude square is like 10 to the power minus 9. So this green dot, and they could remain nearly scale invariant in the sense that they would have almost same amplitude at all frequencies. This is possible. Or another possibility is, even though for long waves you have small amplitude, for short waves the amplitude could be very high, several times higher. So here is the amplitude of long waves, here is the amplitude of short waves. So at short length scales, the amplitude of fluctuation it could be so high, then you can form primordial black holes if this condition is satisfied. And in this article which I asked you to read, I explain you how that condition could be satisfied in a mechanism. Okay, so I'll leave you with that. These are advanced topics, and if you have questions, then only I'll answer that. I'll leave you with that. Here are some links for your future. If you want to read more about it, I've given all the links here, so you can just take a screenshot later of this and figure out. I've given the locations here, or you can send me your questions in my email ID. I want to end by this two remarks. First remark is a black hole. In classical physics of Einstein's gravity, a black hole is a perfectly spherical, nice, symmetric object which absorbs light but never emits. Okay, so that's what great Indian physicist who was also Nobel laureate Subramaniam Chandrasekhar told about black holes. Okay, he really loved black holes, but he looked at them as classical objects. But then Stephen Hawking said no, but if black holes are smaller, quantum mechanics could get important, and these black holes will radiate, and so the black holes are not really perfect, smooth black objects, but they are very quantum fluctuating objects with glowing. So light is coming out of the black hole. So that's the that's the change in our conception of a black hole. So it's a paradigm shift from a perfectly classical, stable, dark object to a quantum mechanical, chaotic, light emitting object. So it's one of the most important objects in physics. Okay, so I'd like to stop here. If anyone wants to ask a question or something, or I don't know how it works here in this platform, but
Sir,
hi, yes,
sir, one student have doubts are in chat box.
I'd love to answer. Can you read the questions to me? Then I can answer.
How long does it take to make a black hole?
Oh, great. Good. So see, our universe was in a plasma state, and the plasma state cooled down to form neutral atoms, and these neutral atoms started getting collapsed. So they started to clump to form stars, and these stars, when they die, they form black holes. So if you want to form a black hole in this mechanism, you have to wait for 300 million years. Okay? After 300 million years, a star will collapse. The star will collapse over a period of several years or so, and then it will form a black hole. But if they are primordial black holes, they are forming right in the early universe in the plasma. So plasma is just collapsing and forming. So depending on when they form, that much is the time it takes to form a black hole. So if you go to these times which I showed you, If a black hole is primordial black hole and solar mass, it is formed within 10 to the power minus 6 seconds. It's just formed in a fraction of a second. A black hole is formed. You have a Himalayan mass black hole. It's formed in 10 to the power minus 23 seconds. So yeah, they could form very quickly. So it depends on whether they were formed by collapse of stars or by collapse of plasma density in the early universe. So answer depends on that. Okay.
Anyone have doubts? Sir, can you end the session, sir?
Sure, we can end. So you can
Uh,
go and read these things. People who want to understand more, you can just read these links. Okay. Thanks.
yeah, okay. Thank you very much,
Thank
Mr.
you very much.
Swagat.
Thanks.
That is a wonderful session.